Welcome back to AE 3530, System Dynamics and Vibrations. In this video, we're going to go through Newton's second law. And I just wanted to first point out that in the previous video, we were looking at springs in series. This type of analysis can also be done for dampers in series, and then you'll find a similar relationship for an equivalent damping coefficient. Okay, so now considering Newton's second law, for a force acting on a particle or on the center of mass of a rigid body, the acceleration is in the same direction and is proportional to the force and inversely proportional to the mass. So we can write that the acceleration will be equal to the force divided by the mass. Or in vector form, we'll find that the sum of the forces is equal, vector forces underlined in this, I'm going to use underline to represent vectors in this class. The sum of the forces is equal to the mass times the vector acceleration. And this is true for translational motion. We're going to deal with rotational motion after doing some examples for translational motion. In this class, you're going to use what I call a problem-solving algorithm to apply Newton's second law. This is really just a solution technique. There's no programming or anything like that involved here. I just use the word algorithm because it's quicker to say than solution methodology or technique. This approach breaks up solving a problem or finding the equation of motion into two portions. First, as we deal with kinematics, and we're looking to find the acceleration vector. And then the second part focuses on the kinetic, which is where we're applying Newton's second law, doing free body diagrams, etc. So the first thing you're going to do is that you're going to define a coordinate system. And first step then is to choose an origin. This will be a fixed point. And this is where you're going to define a fixed reference frame. Sometimes you're given an origin in a problem. Sometimes there is a very natural origin to choose, such as if you're considering like a pendulum, the point where a pendulum connects to the ground, that would be a good origin. Other times you have to arbitrarily choose your own origin, and then you might need to define dimensions in order to help you with defining position vectors. We'll deal with that as we go. So the second step then is for defining a coordinate system, is to define perpendicular directions. You'll generally use your standard Cartesian coordinates, but there might be times where a polar coordinate system or normal and tangential coordinate system are necessary and useful. Then we're going to determine the direction of positive rotation using the right-hand rule. Using the right-hand rule, this would be for standard Cartesian coordinates, this would be counterclockwise, it would be positive. The second step is we're going to define position vectors for every body in the problem from our origin. First part of this is to draw position vectors for each body from the origin. Draw position vectors for each body from the origin. By doing this, we are using the same fixed reference frame rather than using separate reference frames for each body and then having to relate them through relative conditions. Although you can do that, but we ultimately want to describe everything using a single fixed reference frame and a single fixed coordinate system. The next thing to do is to write out the position vectors using your chosen coordinate system. Write out position vectors using the chosen or your chosen coordinate system. And this is a case where you might need to introduce some arbitrary static dimensions so that you can describe where something is relative to your origin based on its static equilibrium position or its rest position. And we'll see this when we do the examples. I'll talk about this. The third step is to determine the velocity and acceleration vectors for each body. First step is just simply to differentiate the position vectors. Differentiate the position vectors to find the velocity vectors. The second step then is to, well, differentiate the velocity vectors to find the acceleration vectors and differentiate with respect to time. Okay, so these three steps cover kinematics. And really they give us the acceleration vector, which may not be a simple thing. You may not be able to just directly guess what it is by looking at a problem. This is a systematic technique and routine to compute that acceleration vector accurately every time. After that, we are done with the right-hand side of Newton's second law. That's the mass times acceleration. And now we're going to focus on the left-hand side, or the forces. And that's where the kinetics really comes in. So the first thing we're going to do is we're going to draw a free body diagram for each body. And if we need to, we will decompose forces. So we'll say decompose forces as necessary, meaning you're going to break them into components if you need to, into your coordinate system. From there, we are going to apply Newton's second law to each body one at a time. We're going to first write out the full vector equation. So we're going to write out the full vector equation We're then going to split that up into components, meaning that we consider the I and the J components separately. So split into components. And then third, for this step, we are going to simplify as much as possible. And then from there, we're going to put this into a standard form. And that standard form will be where we have some function of acceleration. In fact, let's write this in vector quantities. Some function, in fact, actually we'll write it as position vector, velocity vector, and acceleration vector. And it could also be time dependent. Will be equal to some function, let's say g of t. So what this means is that we'll have all terms that involve position, velocity, and acceleration, and any time varying parameters multiplying those on the left-hand side. And these don't necessarily need to be in a vector form. I mean, we would obviously break this into components. So really this would be something like f of x, x dot, x double dot, and then t for time varying parameters equal to a function g of t. Yeah, in fact, actually, let's go ahead and let's erase the vector form of this. And we'll put here as an example, we'll put this here. Because we're going to have scalar equations at this point, we won't be dealing with vector because we've broken up all of those components. In standard form, we're going to have something like, as another example for like a harmonic oscillator, we'll have mx double dot plus cx dot plus kx is equal to g of t. And we'll put this example down here. That's our example. This is our standard form. Okay, so this approach is what we'll call vectorial mechanics. Because we're using vectors to express the relationship between acceleration, mass, and forces. This technique has some benefits to it in that it's generally a straightforward approach. It's something that you've been exposed to over a long period of time. It has a lot of physical intuition associated with, because you can physically experience what a force is. You can just push on an object and feel the force of that push. So you have some physical intuition for what a force is. You can also experience acceleration and feel what that is as well. So it gives you a lot of this physical intuition. The downside of vectorial mechanics is that it requires very intimate knowledge of the forces and how they're acting, and it requires all of this work to decompose forces. You've got to draw free body diagrams for every body, and so there are some downsides to it. Later in this class, actually in the second week of this class, we will start a technique called Lagrange equation. This is a method from what is called analytical mechanics, which uses energy terms to find equations of motion, and it is much more abstract, but it is simpler to implement and does not require intimate knowledge of the forces and acting on a system, and you can apply it using a single equation, apply it and compute the equation of motions for every degree of freedom in a system, or every mass or object in the system. Okay, we're going to stop the video here, and in the next one we're going to go through the first example.